In this video, I'm going to continue on with the idea of correlation and regression and add on a little bit to what we talked about in the last video. So these are two examples that we looked at, and we found the correlation coefficient R for both of these data sets. And what I want to look at is, we know sort of in general that the higher R is, or the closer R is to 1 or -1, the better the correlation is. But we're actually getting a little bit more than this when we do this process. So if we go to the calculator and run that regression, so I've already entered the data for this first one into the calculator, so I'll do my linear regression. And here's the R value we saw before, but we also are getting an A and a B value that come together to form an equation. And this equation is called the regression equation. So in this case, I'll round these numbers a little bit to make it easier to write down, but we have the equation y equals 0.29x plus 52.1. And this equation is the line of best fit for the data. So if we did look at the data, here is the scatter plot for the homework scores and exam scores. If I go in and graph this just for a visual here, 0.29x plus 52.1. And you don't have to graph this for these problems, but it's kind of nice to see what's going on. This is our line of best fit. This is a line sort of modeling the pattern between these points. Now we noted last time that this R value is really not very high. It's not very close to 1, which is why these points don't really follow the line that well. But the question here is, are they close enough that we can use the line as a model, or are they too far away and we really shouldn't be using this regression equation at all? And the way we make this determination, we can do this in two different ways. The first option is to look at the R value we had, and for this data set this was 0.680. and use the Pearson critical value chart from our book. So this is in the appendix, but it's also in the little pull-out sheet as well. This is a little table of critical numbers for our correlation coefficient. So in here we need to know what n is, which means we need to know the number of data points involved. And then we'll also choose either a 0.05 or 0.01 significance level. So if we come back to the data, there were 8 data points on this homework scores and exam scores piece. So that means that we've got an n value of 8, and then the problem should say what significance level we need, but let's just use a significance level of 0.05 for this one. So looking at our table for n equals 8, alpha equals 0.05, we get a critical value of 0.707. So this critical value is the guideline that we would use to cut off what is considered a good fit or a strong correlation from what isn't. So in this case, any R value that would be bigger than 0.707, we would say yes, that's a good fit. Anything that is less than that and still positive would not be a good fit. So based on this critical value, we would say that there's not enough correlation for this particular data set to be able to use this regression equation to make really reliable predictions. In comparison, if we look at the diamond weight and diamond price example, we know that this was a higher R value. So let's go ahead and look at that regression equation. So I went ahead and just entered this data in for the diamond weights and prices. And here's our regression equation. Okay, and again, if we want to see this visually, we could graph this line along with the data. So I've just entered the equation here, and we already have the data plotted. I've already adjusted the window. So here's our data, and here's that line of best fit. We can see that visually these points lie a little bit more along this line. It's still not a perfect fit. But again, we can say, okay, 0.952, this is a pretty decent R value, but is this good enough? So again, using the same method here, we can look at our R value, the n here, there are 6 data points, so that would be 6, and then if we look in the table for n equals 6, and I'll go ahead and use an alpha of 0.05 again, we get 0.811. So this says that if our R value is bigger than or closer to 1 than 0.811, then this is a good fit. So in this case, our R value is big enough. We can accept this regression equation, and now we could use this as a model. So for example, if I wanted to know how much a particular diamond cost, I could take its weight. For example, if I have a diamond with weight 0.6 carats, this wasn't a value that we had in this table, I could take this and plug it in for x in our equation and get a y value that would give us the price. If I put in 0.6 to this particular equation, I come up with 2526.44, so that would be about $2,500 for a 0.6 carat diamond according to this model. The other option here, so if we're not going to use the critical value chart, we can also do essentially another hypothesis test using the calculator. And what this looks like is if you already have your data entered in, so right now I have the data entered in for the diamond question, we can go into the stat tests option and go all the way down towards the end of the list here. There's one called lin-reg t-test, so this is our linear regression t-test. And if I select this, it'll input the data from lists 1 and list 2, which we've already inputted. The frequency and this claim should be fine as is, and then I'll just hit calculate. And here we go. We have some familiar components here and a few unfamiliar ones, but here is our p-value. So in this case we're looking at a p-value of 0.00339, etc. And this is the same kind of thing that we looked at with hypothesis testing. So if we're dealing with an alpha value of 0.05 or even 0.01 in this case, this is a small p-value, so we would reject the null hypothesis. And the null hypothesis essentially says that there is no correlation, or at least not enough correlation. And we would say that, that this is a good model, or that there is correlation between the two. If we did the same thing with our first set of data, we likely would have a p-value that is greater than 0.05. So either method really works. I think you may be expected to see both of them on the homework. One last component here, so if our regression equation is a good fit, we can use that to compute other values. But if not, we really shouldn't use the regression equation. So say we're looking at this homework scores and exam scores question. If I have a homework score of 87%, for example, and I want to know what I'm going to get on the exam score. We already determined that for this set of data, the regression equation was really not that accurate. So to use that to predict my score doesn't really make sense. Now, if it had been a better fit, that would make sense. But if the regression equation is not going to help us, then the best we can do is just look at all the exam scores and take an average. And if you look in the book, this is the procedure that they suggest. So if we can't use the regression equation, we're just going to estimate using the average. So we would take the average of all these exam scores, and that would be our prediction for the homework score of 87%. So we would give 68.1% on this one. And again, I made up these values, so hopefully if you have an 87% on the homework, that doesn't mean you're going to get a 68% on the exam, but according to this data here, this would be our prediction. So it's important that when you're trying to interpolate data like this, don't just use the regression equation immediately. We have to actually look and see, is that a reasonable description of the data, or should we not use it at all? And that's what looking at these R values is really about. So here's a problem for you to try. I'm going to have you find the regression equation and the coefficient, and then determine whether that is going to work as a model or not. And this is about the number of chirps that a cricket makes versus the temperature. So based on what you find, you're going to try and predict what the temperature is if you have 2,500 chirps per minute. That's it for this video. See you next time.